Hey class, and welcome back to the final installment from Chapter 6. And in fact, it also has a little bit of Chapter 10 in here because we're going to talk about springs. The textbook organizes it a little bit oddly, in my opinion. I think it's important to introduce the idea of springs as they offer another conservative force that can be dealt with in terms of potential energy. So I'm going to introduce you a little bit of information from Chapter 10, talk about springs and work done by springs and elastic potential energy, and then also talk about the concept of power. So first of all, a spring, all right? So here I just happen to have a spring, okay? It takes a certain amount of force to pull or stretch a spring. So if I apply a given force, you might be able to notice that the spring will stretch and the amount of force is directly proportional to how much it stretches. As an example, if I hold this here and hang a 50-gram mass on my spring, it will stretch a certain distance. And if I take that same spring and hang a 100-gram mass, I doubled the force applied to it, and the stretching distance would be approximately doubled as well. And so what we find is we can quantify this in terms of an equation known as Hooke's law that tells us that the force applied to a spring is directly proportional. K is the value to represent that proportionality, which we'll define in more detail here in a minute, multiplied by the distance that it stretches. So that K value is known as the spring constant, and it has units of newtons per meter. If you look at our equation, newtons equals newtons per meter times meters. So that's in terms of the force applied to the spring, and the force from the spring back on the object is just equal in magnitude but opposite in direction. So if you notice, if I go ahead and hang my 50-gram mass on here once again, the spring stretches down and the spring is applying an upward force. So that negative sign, it confuses people a lot. All it means is that the direction of the force, in this case up, is opposite of the direction of the displacement or stretch, which was down. So this minus sign just means that the force and displacement are opposite. Your K value, that spring constant, is always a positive value. I never want to see you solve for a spring constant and have it be negative, okay? Because again, X and the force from the spring are just opposite in direction. Here's an interesting concept. So I have my spring once again here. If I were to take this spring and cut it in half, what do you think would happen to the spring constant? Would it be the same? Would it be different? Would it double? Would it be half? What would happen to the spring constant? Pause it, think about it, and let me know. Okay, hopefully you paused it and thought about it. Let's investigate this together. So again, just to remind you, our equation tells us that the force exerted by a spring is equal to negative spring constant times the displacement. So if we were to solve for K, the spring constant is just going to be equal to negative force of the spring over the displacement. Okay, so let's consider how the spring constant might change. So here's my spring that I have, my example. I'm not going to cut it in half, but I will do something similar. So if I hold it from the very end, it stretches a certain distance, all right? So there's a force, which is going to be basically 0.5 newtons, and a certain displacement. I could use that to calculate my spring constant. Now I take the same spring and I cut it in half, all right? So we're half as long. I do the same game. If you notice, same force, same mass, now it has half the displacement. So this is smaller after cutting it, therefore my spring constant is going to increase. In fact, it would double. Pretty weird, just cutting it in half makes it double. Something we'll learn about later on in class, check this out. If I pull this down, it bounces up and down at a certain rate. The rate at which it bounces up and down is directly proportional to the spring constant. So if I were to cut it in half, watch this. It instantly starts bouncing up and down faster just by changing the length because I increase the spring constant. I go back to the top, it bounces up and down slower. I cut it in half, and it starts bouncing up and down at a higher rate. Pretty cool, huh? Physics rules. I love this stuff. All right, so that's a conceptual question for you all. Again, Hooke's law, to be really clear, this is from the beginning of chapter 10, tells us that the force exerted by a spring is equal to negative K times X. Now there's limits to that. If I pulled my spring far enough, eventually the material would start to permanently deform. It would bend. You've probably done that with a slinky when you were young and see how it's damaged as a result. Okay, so just a quick example of how we use this equation. Here's a fun one. We have somebody who's doing Weight Watchers on a diet or something. So she has her spring scale. She decides she wants to calibrate her spring scale, figure out what a spring constant is just in case anything ever goes awry with her scale. She can always go back and check. So let's say that she weighs 135 pounds, which is approximately 600 newtons. She steps on the scale and watches, and it actually shrinks or compresses by 1 centimeter exactly. All right, so maybe she set her phone up with a measurement app and watched this occur off to the side. And believe it or not, most bathroom scales use highly calibrated springs like this, okay? So she stepped on it. What's the spring constant? Try it out. Okay, hopefully you tried it out. Pretty straightforward, right? Hooke's law tells us that the force from the spring is negative K times X. So solving for K, just as we did on the board, it's equal to negative F divided by X. In this case, the force is 600 newtons, and the X is negative 0.01 meters because it's going down, compressing by 0.01 meters or 1 centimeter. So you do the math, and the spring constant is quite large, 60,000 newtons per meter. Boom, box worthy. Or approximately 60 kilonewtons per meter is another way to express that. All right, so spring force, that's fun and something that you can add to the information we learned back in chapter 4. But what does this have to do with all this work energy stuff that we've been dealing with? Well, a spring being compressed or stretched can do work, right? If you have a spring here, right? And if you stretch it out, I pull it down, and if I let this go, the spring's going to pull up on the mass and cause it to accelerate, cause it to gain velocity, cause it to gain kinetic energy. So if I pull the spring down and it keeps wobbling up and down, look, its energy keeps changing. So if it's going from up at the top, you have gravitational potential energy. In the middle, when it's moving, it's kinetic energy. When it's down here, what form of energy does it have? If it's stretched, at the instant that it's its very lowest, let's watch. At the instant that it's its very lowest down here, its velocity is 0, so it doesn't have any kinetic energy. It's down at the bottom, so gravity's not pulling it up. That would be weird. Okay, so what does it have? Well, it has a new form of potential energy, energy that's stored in the spring, and that's known as elastic potential energy. So what we can do is look at work done by a spring, looking at force and displacement. You have to actually do calculus to really derive the equation that I'm going to give you. But what we find is that the work done by the spring is going to be equal to 1/2 K x initial squared minus 1/2 K final squared. Or, since the spring force, as I mentioned at the very beginning of the video, is a conservative force, guess what? You can instead define it as in terms of elastic potential energy. So if I have this spring, if I stretch it out when it's down at its lowest point here, it has stored potential energy. Elastic potential energy equal to 1/2 K x squared. Important thing about the x value, I probably should have mentioned this earlier. Notice my spring has a certain length when there's nothing on it. That's its initial length. Okay, so let's say that right now that initial length is approximately 3 centimeters. I hang this and it stretches. Let's say that this is now about 10 centimeters. X would be 7 centimeters. It's the stretch, not the total length at the end, but just how far below where it started it was. So the amount of stored potential energy in a spring is equal to 1/2 K x squared. We're going to use this in a couple sample videos that are on Foxtail, other videos. I'm not going to do any more right now for the sake of time, but you'll see a couple different examples that use this idea of elastic potential energy as we go forward. Again, our energy units are joules, okay? As long as you're using newtons and meters for your variables, you'll get joules out. All right, the last thing I want to talk about here as we wrap up chapter 6 is the concept of power. So power is the rate at which you use energy or the rate at which work is being done. So when you think about rate, it's kind of like a speed in a sense, right? You can think of it as being the amount of work done in a given period of time. And so power, average power, is work divided by time. I specify that it's average power because the rate at which work is done can vary over time, and to have it instantaneous, you have to use calculus, not dissimilar from what we've seen in the past. Okay, so it's work over time. What units do you think that's going to give you? Well, work is joules. Time, we usually use seconds as the SI units. So a joule per second gives us watts. So if you're ever trying to remember and you think to yourself, what are the units of power? Well, you just told yourself, what are the units of power? So there you go. Cool. So power, again, is change in energy over time. There's a fun little conversion factors that you might use. Horsepower is a common rate of power or unit for power. That's equal to about 1 horsepower is about 746 watts. Also, another unit used in the American system is foot-pounds per second. It's kind of a weird unit, but it's used a lot with engines and stuff. So 550 foot-pounds per second is 1 horsepower. So you can also get a conversion factor there between watts and foot-pounds per second. Another cool thing to observe, so power, again, is work over time. Work is force times displacement, right? So you have force times displacement or distance over time. Distance over time is just velocity, average velocity. So power can also be represented as a force multiplied by an average velocity if you're looking at the amount of power of something as and force is being applied to it and it's moving. Cool. So one example problem I want to wrap things up with here. So imagine that you have a dam, all right? You block that dam to generate electric power. Here in Oregon, a huge percentage of our electrical power used in houses and so on comes from hydroelectric energy, from energy stored behind a dam. So let's imagine that you have a dam and it's allowing water to fall through your turbines and it's using that to spin these turbines, which generates the electricity that we use in our houses. Okay, so let's say that you have water and let's say that it's 57,000 kilograms of water are falling through your turbines every second. Let's say they start at a height 19 meters above and fall down through your turbines. Now, this isn't exactly how it happens, but for simplification, let's say that you have 19 meters worth of potential energy falling through your turbines, all right? And now turbines aren't going to be completely efficient. We're going to say, let's say that they're 50% efficient. So 1/2 of all the work done is actually turned into electric energy, which that's really probably a pretty optimistic number actually. 2 questions for you. 1, how much power would be generated? So what's the rate at which energy is being generated? And question 2 is, how much energy is produced in a single day, assuming that it's ran for like 24 hours? So pause this and try it out. All right, hopefully you tried it out. If not, pause for real this time and give it a go. So let's look at this, okay? First of all, for part A, we want to figure out the power, right? Power, which is work over time. What is the work being done? Well, the work is change in energy, right? So the only thing that's giving energy to our system, that's doing the work that generates the power, is gravitational potential energy being turned into electrical energy through the turbine, right? And so you have mgh worth of potential energy you start with, but only half of that is harnessed, so we have to divide by 2. So we have mgh over 2 as our work, and so our power is just going to be mgh over 2 divided by time. Okay, well, let's see, we have a mass, we know g, and we have a height, but what's the deal with time? And do we really have a mass? Well, no, actually what we have is a mass flow rate, 57,000 kilograms per second. So that's really a mass flow rate, amount of mass in a given period of time. And so if we look at this, in our equation here, we have mass over time, and it's the mass over time that is 57,000 kilograms per second. And so what we can do is we can do 57,000 kilograms per second times gravity, 9.8 meters per second squared, times our 19 meters. And what we find is that our power is 5.31 times 10 to the 6th power watts. That is a lot. 5,310 kilowatts of power being produced. That would be pretty nice. Can power a lot of homes with that. All right, box-worthy. Part B, so how much energy, how many joules of energy are produced in a single day? Well, power is work time over time. So the work is just the power multiplied by time, right? So in one day, that's 24 hours or 86,400 seconds. So we take our power, multiply it by our time, and we find that in a single day, if we had this dream system hydroelectric factory here, we could produce 4.59 times 10 to the 11th power joules worth of energy in a single day. That would be pretty awesome. All right. So that's a little bit about power. You're going to get to practice this and work with that on the homework and other places. Just to give you kind of some fun examples, this is a table I stole out of a textbook. So average kind of young male, around 70 kilograms. The power, the rate at which they consume energy doing different things. Look at this. Go take a nap, boom, 77 watts. So you're burning 77 joules of energy every second while sleeping. Just going for a walk, cool, look at that, up to 280 watts. Biking, skiing, running, you're burning different amounts of energy. As you can see, each of those, it increases. So you're consuming energy all the time just by living, whether you're sleeping, walking around, even sitting, listening to awesome physics lectures, you're still burning joules and burning calories, which is another form of energy. So anyway, let me know if you have any questions, but that wraps up Chapter 6 with a free bonus sneak peek of Chapter 10 in there as well. Have a box-worthy day.